if we consider a simple charged object, and this object is in an external field, then we know that the force on the charge is equal to Q E external, and that will help us to set up and compute the dynamics of the particle by using Newton's second law. And so in that sense, a point charge in an external field, we can only talk about forces. But what if we have an extended distribution of charge? And let's consider a very special case where we have a positive charge and a negative charge. And let's imagine that these charges are fixed together with a massless rod. So that way they will move together. And let's put this object in an external field. So we have an external field acting on this object. And I want to consider a very special case first where this external field is uniform. Then we see that the total force, which is equal to Q times E external, that's the first one, minus Q E external, that's the force on the second one. And if I overlaid the forces here, I would have F plus. And remember, this is a negative charge, and that's why that force is in the opposite direction, F minus. And you can see that the sum of the total forces is 0. And so the center of mass will either stay at rest or move at a constant velocity. But there's still more. This will undergo a rotational motion because even though the force is 0, the torque on this object is non-zero. Now recall that when the total force is 0, then torque, which was defined as a sum, j goes from 1 to n, of rj cross fj, is independent of the choice of origin. So how can we depict that? Well, let's draw our objects again, plus and minus. And just to start with, this is a massless rod. And now you can see why we want a massless rod, because this object will rotate. And let's consider the center of mass. And we'll draw r plus, and we'll draw r minus. And we have F. We have E acting on this one, E external. But remember, the force is a little bit different. We have F minus, and up here we have F plus. So what we can see is that there will be a torque given by the cross product. And if we extend this vector r plus, we can see that this will produce a torque in the direction indicated by my thumb. Now, down here, if we extend this one in the same way, the torque there is in the same direction. So both of these objects both of the forces are exerting a torque on the same direction, and that will cause our object to rotate. Now remember, there's no total force on this object. The torque is independent of the point that we want to calculate. And we'll use that fact later on when we calculate specific examples. But for the moment, let's do a general calculation. We know that the torque is equal to the force, so that's Rj cross Fj, and the force is the qjth charge times the external field. And now, even though we only have 2 charges, I can make this an n charges in a system, provided that the total charge on this is 0. The total force, the total charge is 0. So now, in a cross product, this is just a scalar quantity. It can be positive or negative. It's not a vector quantity, so you can move it around. And we're going to put it onto the first term, qj rj, cross. Now, every single term in this cross product has the same uniform E field, which means I can pull it out of the vector sum of this sum over here. And if you recognize here, this quantity makes sense. Again, we're assuming that the total charge is 0. And then this is exactly what we called the dipole moment of the distribution of charge. And so we have the result that if we consider just a dipole, plus and minus, and remember, the dipole moment goes from the negative charge to the positive charge, P, and the whole system is acting in an external field that's uniform, then this dipole will undergo a torque. It will rotate, and it will rotate in that direction. Now, in summary, what we see now is for point-like objects, we can use our Coulombic expression. If we put that point object in an external field, it can experience a force. If the total force is 0, then the center of mass of the object will not accelerate. But if we have an extended object of 2 charges, then that object will experience a torque. And we have a very straightforward way to calculate that torque. One thing to keep in mind is when we get to examples is that, again, we're considering systems in which, in this calculation, the total force was 0.